This is Mrs. Zappia with Lesson 5 from Grade 8, Module 3, the first consequences of the fundamental theorem of similarity. Our essential question is, what is the converse of the fundamental theorem of similarity? See if you can state in your own words what the fundamental theorem of similarity is. Recall that given a dilation with center O, right here, and scale factor R, and O, P, and Q are not collinear, then the segment connecting the original points, which would be right here, is parallel to the segment connecting the dilated points. So if we dilated the points, P and Q according to a scale factor, then P prime would be down here and Q prime would be down here. And the theorem states that the segment connecting the original points will be parallel to the segment connecting the dilated points. So we have P prime Q prime is parallel to PQ, and the length of P prime Q prime is equal to the scale factor times the length of PQ. So let's talk about the converse of a theorem. The converse means the opposite. The converse of a theorem begins with a conclusion and produces a hypothesis. Here's an example of a converse. And sometimes a converse is true and sometimes it's not. For example, if it is raining, then I have an umbrella. And its converse, if I have an umbrella, then it's raining. In this case, the converse is not necessarily true. An example where the converse is true. If we turn the faucet on, the water comes out. The converse is, if water comes out, then the faucet is on. That's a converse that is true. The converse of a theorem is basically the work we did in the last lesson, but backwards. In the last lesson, we knew about dilated points and found out that the segments between the points and their dilations dilated according to the same scale factor. We also discovered that the lines containing those segments were parallel. The converse states that we're given parallel lines, and one line is dilated by a scale factor. With that knowledge, we can say something about the center of dilation and the relationship between the segments. Add this to your notes. The converse of a theorem begins with a conclusion and produces the hypothesis. The converse of the fundamental theorem of similarity begins with a statement about parallel lines. If PQ is parallel to P prime Q prime, and P prime Q prime, the length of P prime Q prime is equal to a scale factor times the length of PQ. If this is true, then from center O, P prime is the dilation of P, and Q prime is the dilation of Q. Then we would know that the length of OP prime is equal to the scale factor times the length of OP. We would also know that the length of OQ prime is equal to the scale factor times the length of OQ. Let's take one more look at a diagram for the fundamental theorem. The fundamental theorem says that if you dilate the length of OP using a scale factor, and you dilate Q with the same scale factor, then you will end up with parallel lines. The converse says, let's draw the diagram. The converse says that if you have parallel lines and the length of PQ, which is the length down here, if the length of P prime Q prime is equal to the scale factor times the length of PQ, then from center O, we have a dilation of P and a dilation of Q. And then we know that the length of OP, which would be here, the length of OP prime would be equal to the scale factor times the length of the original segment, and that the length of the dilated segment would be equal to the scale factor times the original segment. So again, the converse of the theorem starts out backwards, or at the end, and starts with parallel lines. Let's take a look at exercise 1. In the diagram below, points P and Q have been dilated from center O by a scale factor of r, and the length of PQ, or rather the segment PQ, is parallel to P prime Q prime. The length of PQ is 5 centimeters. The length of P prime Q prime is 10 centimeters. Now, in your book, the point O may not be labeled. So would you take a centimeter ruler and mark and label where O is? So take your centimeter ruler and line up the end of the ruler with P prime. Put it through P and then measure to 6 centimeters. And that's where your O point will go. Now we're ready to move on to our next step. Part A, determine the scale factor of R. Taking a look at the information given, we see that the length of PQ is 5 and the length of P prime Q prime is 10. So we know the length of these two segments. So we want to determine the scale factor. Recall that the scale factor can be determined by writing our equation. The length of P prime Q prime is equal to the scale factor times the length of PQ. We know the length of PQ prime is 10, and we know the length of PQ is 5. So the value of R, or our scale factor, is 2. You can also find the scale factor with a simple division of the dilated segment length over the original segment length. Either method will find you your scale, or your scale factor R. Part B. Locate the center O of the dilation. Measure the segments to verify that OP prime is equal to the length of OP times the scale factor R. So let's draw our rays from the center O through the point and the dilated point. Whoop. There we go. And then we'll draw a ray through O and Q and its dilated point, Q prime. Now, we know, according to these equations, the lengths of the segments, and we're going to verify that with measuring. I'm going to pull my ruler over and I'm going to measure my segments. The length of OP prime is equal to the scale factor times the length of OP. On our ruler, I can see the length of OP is 3 centimeters. Our scale factor is 2, and the length of OP prime is 6. And that verifies that our theorem works. Then we can also show that on the right side of the triangle with the segment length OQ prime equal to the scale factor times the length of OQ. Pause the video and complete this part of the problem. So what we did in exercise 1 is we verified the validity of the converse of the theorem. We proved it to be true. Example 1. In the diagram, we have center O and ray OA. We want to find the coordinates of A prime. We're given that the scale factor of the dilation is 2. So we're going to dilate A from the center O with a scale factor of 2, and it will end up out here somewhere. And we don't know exactly where it is. To find A prime, we could use a ruler or a compass and measure OA. But now that we know about the fundamental theorem of similarity, we can do this another way. First, we should look for parallel lines that will help us to locate A prime. And we can use the coordinate plane to ensure parallel lines because we know that these lines are parallel to each other. We can use the vertical and horizontal axis of the coordinate plane to ensure that the lines are parallel. The coordinate plane is set up so that the lines never intersect. We can also think of those lines as translations of the x and y axis. Therefore, we're guaranteed to have parallel lines. We'll use the x-axis as one of our rays. Where should we place point B on the ray along the x-axis? So here, this is going to be our ray. What we can do is we can drop a line from A to our x-axis, and that will give us the length of the original segment. And we'll call that point B. So now we have a segment called OB. We'll use the length of segment OB to find the length of OB prime. So here we have the length of segment OB prime is equal to the scale factor times the length of OB. We know the scale factor is 2, and we know the length of OB, 1, 2, 3, 4, 5, is 5. So the length of OB prime is equal to 10. This is the x-coordinate of the point for A prime, which is what we're looking for. Next, we'll find the y-coordinate. To find the y-coordinate, we'll use the length of A prime, B prime is equal to the scale factor times the length of AB. We know our scale factor is 2, and we know the length of AB. AB is right here, and we know that that length is 2 because it's on the y-axis marked at 2. And we multiply that together, and that gives us the length of A prime, B prime. This is the y-coordinate of point A prime. So we have an x-coordinate of 10 and a y-coordinate of 4. 10, 4. So right here is A prime. Notice here are the parallel lines that we were using. And our dilated segment, we had the original segment right here of OB, and we dilated it with a scale factor 2 to find point B prime. Let's go ahead and label that as well, B prime. And then we use that to find our y coordinate, which was 4. So there are 2 steps in this process, finding the x coordinate and then finding the y coordinate. We're going to skip exercise 2 for now. Turn the page. Let's take a look at example 2. In the diagram, we have center O and ray OA. We are given a scale factor of dilation 11/7. We want to find the precise coordinates of point A prime. This is similar to the problem that we just completed, where we are going to first find the x coordinate for A prime and then the y coordinate for A prime. Our first step is to find where point B is. So we're going to drop a line from A and we're going to call that point B. This is our segment OB. Right here we are finding our x coordinate. So we start out with the length of OB. We multiply it by our scale factor and it gives us the length of OB prime. We know our scale factor is 11/7, and we know the length of OB because we can count it on the x coordinate. 1, 2, 3, 4, 5, 6, 7. Multiply that, and that will give us the length of OB prime. The length of OB prime is equal to 11. This is our x coordinate of A prime. Next, we'll find the y coordinate. The length of AB times the scale factor is equal to the length of A prime B prime. The length of A prime B prime is the y coordinate because it will take us up to that coordinate. We just haven't found out yet where this line is. Or have we? That would be the 11. So it's over here at 11. And this will be our point, but we don't know the exact coordinate of it yet. Our point will be here. Back to our equation. We know that the scale factor is 11/7. So we'll substitute the r for 11/7. The length of AB. The length of AB is right here. And we can count that. That is on the y-axis 6. Multiplying those two numbers together gives us the length of segment AB prime. A prime, B prime. And that gives us 9 3/7. This is our y coordinate of A prime. So A prime will be up here, and the coordinates are 11 and 9 3/7. We used our knowledge of parallel lines. These are the parallel lines. We know that they were going to be parallel because they are on a coordinate plane. Then we found the length of segment OB. We dilated it according to the scale factor given and found B prime. Then point A prime is the length of this segment, A prime, B prime. To find the length of this segment, we used our equation. The length of AB prime is equal to the scale factor times the length of AB. So then we went over here and we counted the length of AB to be 6. Multiply it by your scale factor and get your answer for your y coordinate. Then write your A prime coordinates as an ordered pair, and that is the precise coordinates of A prime. We're going to skip ahead to the summary. Turn your page. In this lesson, you have learned the converse of the fundamental theorem of similarity. If line PQ and P'Q' are parallel, and the length of P'Q' is equal to the scale factor times the length of the original segment PQ. Then, from center O, we will have P', which is a dilation of P, and Q', which is a dilation of Q. And we will know that the length of OP' is equal to the scale factor times the length of OP, and OQ' is equal to the length of the scale factor times the length of OQ. To find the exact coordinates of a dilated point on a coordinate plane, we use what we know about fundamental theorem of similarity, dilation, and scale factor.